Your evals should not just report scores. They should decide whether the LLM system ships or gets blocked. This is the workflow you'll know how to run when we're done, which scores regression cases and gates the release on a quality floor. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. LLM evaluation is more than a single number. Teams need concrete pass-fail signals for high-stakes cases. You want automation that surfaces regressions, gives partial credit for near misses, and forces a human and an automated gate to agree before shipping. That is what an eval harness delivers. It turns a set of examples into deterministic checks you can run in CI and trust when a prompt update or model change arrives. At a high level, we score each example two ways. One is a hard exact match, so critical answers never drift. The other is a soft string similarity, so near misses still get credit. We then weight cases by severity, so high impact tests carry more influence than low priority ones. This balance lets teams push small improvements quickly while blocking catastrophic regressions. We will build a tiny harness that defines cases, scores baseline and candidate prompts, rolls per case and run level metrics, and finally computes a binary release decision. It is small, deterministic, and easy to plug into a continuous delivery pipeline. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a shared set of cases and a simple baseline so we can see what passes today and what fails when we change the prompt. This snippet establishes shared eval cases and measures how a baseline prompt performs with exact matches. The dictionary cases holds each scenario keyed by a short identifier along with its expected answer and severity weight. Baseline maps those IDs to the outputs returned by the current prompt, so we can iterate the same order every run. A list comprehension builds matches by comparing each expected answer to its baseline counterpart, and dividing their sum by the length yields accuracy. The resulting baseline accuracy equals 0.50, shows only half the cases clear the hard gate, warning that manual review is still required. Now that we have a baseline and know where exact matching fails, we add a soft scorer, so near matches get partial credit and we can rank prompt variations more fairly. This example introduces eval run, so we can score each case with both exact and SequenceMatcher soft metrics. Inside eval run, we iterate the shared cases dictionary, pull the candidate output from baseline, and compute a ratio-based similarity with SequenceMatcher. Every iteration appends a dictionary containing the case ID alongside its hard Boolean and soft float, giving downstream steps reproducible per-case traces. Baseline scored stores these records for the current prompt, while fmean summarizes their soft values to provide an aggregate that tolerates partial credit. The mean similarity equals 0.83 print highlights that despite hard misses, lexically similar outputs keep the baseline competitive enough to compare against future runs. With per-case scoring in hand, the next need is to compare two runs so we can tell which prompt variation is better overall and avoid manual inspection of long tables. This code packages per-case results into run-level metrics so we can compare the baseline against a candidate prompt revision. The helper aggregate collapses each scored list into accuracy and similarity percentages without losing the ability to reuse the per-case data later. Can scored reuses eval run with the candidate outputs, and both baseline metrics and canned metrics capture deterministic floats. The best tuple chooses whichever run attains the higher similarity value, letting experimentation pick winners without eyeballing raw tables. The printed best similarity run equals candidate 1.00, confirms the tweak now leads on similarity, flagging it as the current frontrunner. A higher similarity does not relieve us from guarding priority cases. We next add severity-aware gates, so a small regression on a critical case cannot be hidden by wins on low-priority tests. This snippet adds severity-aware gates, so softer regressions cannot hide when priority cases fail. The Gates dictionary sums severity for the passing cases inside can scored and normalizes by the overall weight, so heavily weighted tests influence the weighted accuracy check. A second entry uses min over the SequenceMatcher scores, but filters to severity 1.0 cases, guaranteeing top priority prompts stay above their soft threshold. Pass rate then averages those Boolean checks to deliver a single release gate signal for this run. The release gate pass rate 1.00 output shows the candidate clears every gate, proving high impact coverage remains intact. Finally, we combine comparisons, minimum thresholds, and regression checks into a single deterministic release decision. You can plug into CI to block or allow shipping. This example rolls metrics, thresholds, and gate output into a single release decision. Release ready chains together the previous comparison result, minimum accuracy and similarity standards, regression checks against baseline metrics, and the pass rate from the weighted gates. By writing the conditions inline, we maintain a deterministic Boolean that can drop straight into CI or deployment automation. When any predicate fails, the expression flips, immediately blocking the release without manual spreadsheets. The release decision equals ship. Message confirms every guard passed, signaling the harness would allow this prompt change to ship. In a real product, this toy harness maps directly to automation. The same checks become CI steps. The per case records become triage tickets. The weighted gates map to on-call paging for critical regressions. Recap in 3 quick points. What it is: a repeatable eval harness that computes hard and soft scores per case and combines them into a release signal. When to use it: when prompt or model changes must be validated automatically, and priority failures cannot be missed. One caveat: string similarity helps, but it cannot replace semantic understanding for subtle failures. So keep representative high-quality cases. Next step: scale this exact approach by adding timing and accuracy checks on a larger corpus, and build an approximate nearest neighbor index for fast similarity at scale. If practical, automated AI engineering helps you ship safer models. Subscribe and watch the AI engineering videos.